I'm one of the solution architects for Amazon Web Services. I appreciate everybody's patience. Timing for this stuff is always fun. I'm going to present today, together with some esteemed colleagues, on Elastic Block as a service, using EBS, how to gain best benefit from EBS, understanding the difference between EBS standard and provisioned IOPS, and applications to large-scale workloads. So, as we get started, really please appreciate everybody's feedback. A lot of the presentations that are happening today, this is the very first time they've been shown anywhere. And so the more we hear from you, whether this is valuable, not valuable, needs correction, it would be easier if it was faster, any of that kind of stuff, bring that information to us. We're really looking forward to continuing to iterate and innovate on your behalf. There's quite a lot, I think, to cover, so I'm going to jump into it pretty quickly. Hopefully this isn't an unusual or confusing slide for folks. EBS is not a hard drive. EBS is a service from Amazon, a service that allows you to consume POSIX storage, which means block storage. It's the kind of storage you can put file systems on. That may be cursory to some folks, but for others, it's important to rationalize the difference between a service where you're able to consume storage on demand when you need it, an extra device present in your instance, versus a physical disk where you're going to the store and unwrapping the thing and dealing with the vagaries of that. Another sort of difference there, an important part about what makes EBS the service, not a disk, is that it has very different characteristics than any physical drive you can go buy or any physical device that serves drives to other things. So EBS is not a SAN, it's not a NAS, it's not a DAS, it's not any of those other kinds of things. It's its own product built by AWS for some very specific purposes. We worked very hard at the very outset of the design of EBS to ensure that the #1 goal was met. And the #1 goal for the design of EBS was making it so that EC2 instances booted really, really fast. Everybody like it when EC2 instances start quicker rather than slower? Me too. So we knew that that was a thing that enabled people to test faster, enabled applications to get off the ground more quickly, and it was really driven by sequential throughput off the disk. How do I get the reads out of there as quickly as possible? And there's also the use of those volumes as the root storage for swap. So lots of bursts of short duration but random activity. And so you'll see EBS as a device, as a service, was really built in that context, built to serve that workload. And what we found is that people, once they got a taste of disks you can move from instance to instance, volume devices that can be provisioned the second that you need them when your software asks for it, that they'd use it for a lot of other stuff. So going forward now, years after the release of this product, EBS has been used for everything that you can use hard drives, physical devices for. On EC2, relational databases, SQL Server, MySQL, Oracle gets built on top of EBS storage. The RDS product consumes EBS storage, uses that as a system to make sure that you have high-performance, consistent storage. NoSQL databases, MongoDB, Couchbase, Riak, Voldemort, all these sort of different tools take advantage of POSIX storage, need the POSIX locking mechanisms and other controls that are present in file system-based storage to provide the great value that those applications do. Data warehousing applications, you heard today about Redshift and some other workloads there. Files, the movement of objects around media content, all of these different services depend on the applications that access storage. So another big driver for that sits beneath all of these is the use of existing application software, whether open source or not, to access disk storage. So a lot of us don't have the opportunity to rewrite the database that we use or to change the structure of how it is that our storage is accessed by applications. So we've found that there are lots of workloads that make sense, and those workloads really haven't changed. So we changed disk. We made this abstraction, EBS, that's different than a standard physical disk, but your workloads haven't changed. They haven't adjusted. And so it's important as a system designer, as a DevOps operator, as an engineer trying to build high-performance scaling systems on AWS, that you understand the behavior of those tools. So a couple of quick definitions. I'll be using these terms pretty frequently in the next couple of minutes. IOPS, the number of operations that you do to disk or to disk services like EBS per second is a critical measure, in particular around random workloads. The workloads that now provisioned IOPS is maybe a better use case, a better fit for those use cases. We've also spent a lot of time and talk, and we'll go through and show examples of what throughput looks like. The number of megabytes you can stream down to or read off of a disk per second. Latency, the delay between individual reads or writes, or how long it takes to receive the first bit of a read. And then capacity, the actual amount of storage that you provision. So those values aren't actually present, you'll note, on this hard drive, which is a physical device. You can buy it from the other Amazon service, Amazon.com. So Amazon.com will sell you a physical hard drive, and it has all of these numbers on the package. On the back of the package, it describes things like the number of sectors per track, and the number of cylinders that are part of the head, and all of these other sort of mechanical vagaries that I spent a lot of time, I'm sure you did as well, studying their impact in the performance of your applications. You'd learn what all those numbers meant in terms of how many actual IOs at what block size could I get, how much latency would be received, how should I configure the file system that gets deposited on the disk. So on EC2, when you use EBS, we don't have a back of the box. That data isn't the right set of information to use to evaluate the application's compatibility with disk, with compatibility with the performance of our disk or the behavior of our disk. The right things to use is the information that we share about those services. So we have two different disk subsystems, two different approaches to delivering storage as a service to your applications. First, and the one that we'll spend a lot of time sort of talking about the details of, is provisioned IOPS. So provisioned IOPS is a service where we're delivering not only the ability to provision the storage capacity, the number of gigabytes that you need, but the IOPS capacity, the amount of read and write transactions per second that you can achieve on disk. We'll allow you today to provision up to 2,000 IOPS for individual EBS volumes. That's a big number, just for context. When we talk down in a little bit, standard EBS storage over a steady state tends to operate in the range of 100 IOPS. So at 2,000 IOPS, that storage performance is something that we've set as a provisioning marker, as a target. You've told us how fast you want it to go, and it's the job of our service to deliver that speed. So we set an expectation with you about how fast that will go. So we'll provide up within 10% of what you asked for, 2,000 IOPS, so that'd be between 2,000 and 1,800, 99.9% of the time. So that's a very, very high service standard. It's a very high level of performance and a high level of consistent performance. One of the earliest things we heard in feedback about EBS wasn't that it wasn't fast enough or that it didn't meet the needs of certain workloads. It was that it changed, it varied, it had variable performance. And that variability was actually a part of the core design to allow it to do the bursting that made EC2 instances boot so quickly. So we've also constructed provisioned IOPS to have a very specific target block size. So it wants 16K block operations. You can write smaller than that block size, you can write larger than that block size, but that's the unit that our service counts as an IO. And as a result, there are some tricks that you can do to make your specific application, if you know a little more about the details of how it works, fit into our storage from a performance standpoint. The design of provisioned IOPS was built around the concept that each individual IO is metered from a service time perspective. So if you provision 1,000 IOPS EBS volume, each one of those individual IOs is supposed to take a millisecond. That's the way that it was designed, and it's the way that we control the performance of each of the volume subsystems. Provisioned IOPS, like standard EBS, allow up to 1 terabyte of storage per volume. Of course, those can be aggregated with multiple volumes. EBS, to contrast it with provisioned IOPS, really provides a much lower density of IO per storage provisioned. So at roughly 100 IOPS steady state, with best effort bursts into the hundreds, EBS volumes do great, again, for variable, bursty workloads that have change built into their sort of behavior, and are, frankly, they're less expensive. So if you have some workloads where the behavior fits with standard EBS, that's a product you should continue to take advantage of. If you're already doing the work of aggregating multiple EBS volumes to try and squeeze performance out of the EC2 system, really encourage you to take a look at provisioned IOPS. So EBS also provides, as a ratio, a higher degree of throughput per gigabyte provisioned in comparison to provisioned IOPS, and also delivers a kind of latency that's different. So it's much slower per individual operation than provisioned IOPS, typically in the 10 millisecond range or less for write operations and the sort of 20 millisecond range or less for read operations. So both the same size, but both sort of very different products. You'll note, I've said a bunch of the sort of specifications about how these things work, but there's a very large asterisk in the upper corner. We should probably talk about what that means. Provisioned IOPS was designed as a service specifically around the workloads of relational, non-relational, and high IOPS storage. So we found, and when we worked out the design of this product, one of the core pieces that we heard back from customers was the drive for consistency. And the consistency of performance, from our perspective, meant that every individual I/O should be a consistent experience, not just the average of hundreds or thousands of them. So we did meter at the individual I/O level. And the result of that is that each I/O transaction has a service time, has a specific latency is another way of thinking about it. So that operation then is valuable. It's a resource. You actually pay for it in advance. You provision the amount of performance that you'll receive. And as a result, any one of those individual I/Os that you don't take advantage of are lost. They're lost forever. So the service doesn't say, well, he didn't write 500 I/Os this quarter second. I'll just give him 500 I/Os in the next quarter second to make up for it. Nice if it did that, but that's just not the way that it was designed, because what we heard from customers is they wanted each individual I/O to go at the same speed. So a really critical driver of the performance of being able to extract every one of those individual I/Os from a provisioned IOP volume is queue depth. You have to have enough work available so that at every next millisecond, an individual I/O operation is waiting to be completed. So there's a ratio there that's important to understand. So if you have no queue depth, there's very little latency between the individual operation that you ask for and the response to that operation from the provisioned IOPS volume. So if you are delayed by a couple of milliseconds, 50 milliseconds, 100 milliseconds in bringing a piece of work to provisioned IOPS, it doesn't do any work for you. But once it gets there, there's nobody else in line in front of you. So you'd get that response back in that very next millisecond. In a longer queue depth, in a larger number of workload units that are provisioned, you could potentially add latency to your transactions. If you have hundreds or thousands of I/Os in a deep, deep queue waiting for the provisioned IOP volume to work, it's necessarily going to take a long time to get through to those pieces. So important as you're tuning the configuration of your applications to line up the right level of queue depth to the workload that you're using. Another important complexity, important sort of differentiation between the behavior of provisioned IOPS as a metered service in comparison with EBS as a best effort service. The individual blocks are 16K. That's the size. So if your application, which communicates to our storage layer over network connectivity from EC2 to the EBS network, that connectivity is provided by the EC2 network, and every instance provides a certain amount of network bandwidth. So that bandwidth is not IOPS sensitive. It doesn't really care if you're sending 1,000 distinct transactions or one big transaction that's 1,000 times the size. That's a throughput versus IOPS measurement. So it's important as you're designing the number of EBS volumes, the size of them, the amount of data you're going to move back and forth, that the ratio between the instances and their size and their network performance and the EBS performance capacity, how many IOs you could achieve, is matched up. So we built a service. We built an addition to EBS to allow you to be very, very specific about exactly how much throughput to EBS EC2 provides. That's called EBS optimized instances. So by adding that checkbox, you're able to make it so that an EC2 instance has a very specific amount of throughput. So M1 larges receive 500 megabits, M2 4XLs, M1 XLs receive 1,000 megabits of throughput. So if you have 1,000 megabits a second, you can move 1,000 1 megabit blocks per second, but EBS won't take a 1 megabit block. It wants a 16 kilobyte block. So you have this mismatch. You could use that 1,000 megabytes of throughput to write very large blocks, in which case you'd have to have a very large number of provisioned IOPS volumes to spread those blocks out across the individual 16K operations that it would write to disk. Or you may be writing very, very tiny little transactions, not even 16K, maybe 8Ks, like are the standard for SQL Server, or down to 4Ks, like are standard for MongoDB, even 2Ks for some sort of block device operations in file systems for Windows, things like that. So if you're focused on even smaller workloads, the number of IOPS that you provision may not be the right measure to attend to. You have a 2K IOP or a 16K IOP, we don't really care. You still get 1,000 of them if you provision 1,000. So 2K IOs, 1,000 of them a second, is only 2 megabytes through the disk, through the network. So you could provision even more storage to consume the IOPS capacity that EBS can provide than just the sort of normal ratios that I think were standard in normal EBS of 4 disks or 8 disks or something like that. So we're seeing more exotic topologies, folks running 10s and 15s and 20 volume deployments to take advantage of the number of IOs you can extract from the EBS service and from the EC2 provisioned IOPS service. So RAID becomes an incredibly important part of how you configure for that. We have a lot of experience both with MDADM and LVM RAIDs, as well as in the Windows world using disk management to construct striped volumes. There's a lot of debate and dialogue about the difference between RAID 0 and RAID 10. It's kind of an open discussion. By and large, if your application handles durability and resilience at the application tier, we recommend RAID 0 as the best method to extract as much performance as possible, both read and write performance, from the disk subsystem, the most efficient way to build. Since you probably want multiple instances deployed in our best practices to distribute workloads across availability zones anyway, makes sense that you would move the redundancy up to the application tier. On the flip side of that, if your application doesn't easily distribute across multiple instances, or if a class of downtime is being able to work through a downtime by manual repair of an instance is a critical part of the design of your topology, using RAID 10 gives you the opportunity, if you lose an EBS volume, if there's some kind of a problem with it, if it becomes corrupted in the configuration or there's some other kind of failure, they are made out of real world things, and as a result, they're subject to potential failure. RAID 10 gives you the opportunity to restore the durability of the disk subsystem without waiting around for a whole new instance to turn on or triggering the failover of your replication. So in a lot of cases, and here's this sort of interesting thing, in almost all of the workloads that worked on us just 6 months ago, you're able to provision that much performance from provisioned IOPS with a single volume today. So the difference is so big between something like 100 IOPS and working and straining and squeezing to get into the 1,000 IOPS range on EC2 instances, where now 2,000 IOPS is a very trivial thing to deploy, not a lot of complexity there, single volumes attached, and we've moved the state of the art pretty significantly forward. So one team that I've worked with personally that's done a lot to move the state of the art forward just sort of got announced today at our keynote. Hopefully you guys were able to take a quick look at that. Was the work done by the Obama for America campaign. We have one of the members from the Obama for America campaign team here, JP Schneider. I just want to give him a quick minute to say a couple things about how they built on top of AWS using EBS.
Thanks, Miles. Hi, everybody. As Miles mentioned, using EBS actually saved our butts a bit. We had 2 real use cases for it. We had to scale fast, we had to scale big. On the scaling fast part, if you're using instance store volumes today, maybe a little bit of Puppet, you might be looking at 5 minutes to detect that you need to auto scale, and then about a minute to come up, and then about 2 to 3 minutes to build the puppet. What we found was waiting 5 or 10 minutes to scale up when people wanted to donate to the president probably wasn't the best idea for us. So what we did instead, using Asgard and just a little bit of manual EBS work, was we made all of our front-facing nodes into EBS volumes. We bolstered that with a kind of a baseline of instance store volumes, just to make sure that if EBS ever had an issue, we stayed up and everything was happy. On the second use case, scale big, we really didn't do that with EC2 instances. One of the things Miles might mention a little bit later on is that RDS now also supports provisioned IOPS. And unfortunately, we didn't have provisioned IOPS when we started the campaign, but we did wind up being able to take advantage of that. So if in late May there was about a minute of downtime, that was us switching to EBS volumes. Sorry about that. The provisioned IOPS that we used were for both our Narwhal database. You've probably heard a little bit about that in the news. And that is our main data store, or was our main data store. It had a lot of information and was accessed unbelievably frequently. We were in tens and tens of thousands of requests per minute during slow times. And so by using provisioned IOPS with RDS, which is, of course, EBS-backed, we were able to keep that up during the hectic election week, and we were pretty happy with the performance. It was really good. Thanks, Miles.
Sweet. Thanks, JP. Everybody give JP a hand. So one of the applications that I helped with as a part of that workload is what's depicted here, the fairly large analytics cluster. So the upper bound for that, given a distribution across 8 of our large CC2 8XL instances, was significantly in excess of 200,000 IOPS as a performance system, and in several different internal tests, because we weren't sure exactly how much data we were going to receive, we were able to double that on demand. So that puts us into a range where you're really talking about not just the fastest stuff available in the cloud, but some of the fastest stuff. It's a very, very high-scale workload. So one of the things that I want to show, because I don't think it's enough just to sort of talk about it, we should have a couple of quick tempt the demo gods demos. I will show the difference between single volume and multiple volume, and I'll be able to show that in a couple of different ways. So time for a little proof about what this stuff looks like. So first off, right here, dink. So we have this Windows instance in the corner, and you'll notice, can everybody read that in the back, or should I make it a little bigger? Bigger. How's that for illegible and yet bigger? So, almost. There we go. So here's an M24X large instance that's running Windows. That's built using now Windows Server 2012. That was fairly recently announced. Adds a couple of unique features. It's also built here with 10 provisioned IOPS EBS volumes, each with 2,000 IOPS. So that sets you up really something you can provision in our console without any sort of command line code. You just sort of add new pieces, next, 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 and out comes this 20,000 IOPS high-performance device. So what that looks like from a server standpoint is here I'm inside of a remote desktop running PowerShell, connected to a Windows server on EC2. And what I'm going to demonstrate is the difference between slower, my friend here that's deployed only, sadly, on one of our provisioned IOPS volumes, and fast, a disk here that spans all 10 of them in a RAID 0 strike. So it's relatively straightforward to say I want to do work. So this is doing 8K random IOs. That's the standard for SQL Server applications. You can see We're getting right at 2,000 IOPS from a 2,000 IOPS provision volume, and it does it very, very consistently. So I'm doing little 3-second tests, but you're seeing 2055, 2054, 2061, 2054, very, very tight to the specific definition of what it is that you provisioned, number of megabytes a second, all that. Another example of that then, let's see if I'm looking at the right thing here, would be to change it and look at the faster disk. So by going to 10 volumes instead of just one, you do the same test at the same speed, and now you're looking at 19,000 IOs. And you'll be able to do that fairly consistently. Larger number of volumes. We're right at, you'll note here, 155 megs a second. That's fast. We built this this morning in about 4 minutes. It's really not complicated. You start the instance and turn on EBS optimized and attach the disks and install SQL IO and hit build, right? So this used to take quite a lot of work to get to 1/20th this fast. So you can also see ticking along, you can provision any sort of specific size provision IOPS volume that you like. So I've got one over here that's tucking along at 660 is what we provisioned it at. You can see it sort of bouncing around. There's also one, let's see where they're all at. Down here, so this one, let's redo it. So this is a 10,000, these two are on the same box again. Let's take this one away. So this is a 10 gig MongoDB test. This is using Mongo performance. I'll make it vastly larger since it's probably invisible to you. And what it will go through, and we'll take a second because it will go and build this new 10 gigs of totally random data. What that does is generate a test set, and then it uses 16 threads on the local machine to go pound away and do random IOs, this time at 4K operations. So to show you another important measure while it's setting up that test file. So on the Windows instance, if you're back here, the individual volume here, let's take one of these guys, and then go to, come here. You watch this stuff in CloudWatch, and you get a little view into how we depict individual volume performance. There we go. So you can see it provisioned at 2,000 IO. And down in here, we've been running a couple of different tests, but this volume, come on. So down in here, so there's the throughput at 100% go. So it's definitely being consumed. Let's go back in time a bit. 6 hours. So an important piece, we were talking earlier about queue length. So here's the SQL IO test not delivering a high enough queue depth really to saturate the disk. So we might be able to squeeze a little more consistent performance out if the SQL IO test were able to deliver a more consistent or a longer queue depth. You'd also be able to see so here's the IO test. I don't know how many of you folks have seen what these graphs look like on standard EBS. That's maybe something we can do in another talk. But that's basically ruler flat performance in comparison to most network attached storage systems or other sorts of things. That's variability in the sort of single digit percentage marks across the duration of a multi-hour read. So that's a pretty significant success, we think, from a storage performance subset. So this thing is still running. It may take a little longer than we have left for the talk, but if we have an opportunity, I'll come back to it. One of the things I want to point out is these demonstrations are, in fact, the worst conceivable way to benchmark the performance of EBS. As a system, it's more complicated than all of this. So it changes over time. It has variable performance based on all of the different complexities of a multi-tenant network system. And one of the biggest variables of that is time. So AWS adds new server capacity, it adds new regions, it adds new availability zones. All of those different things change the broader behavior of a system that products like provisioned IOPS are doing everything Amazon knows how to do to compress the performance of down to a very specific, very reusable unit. EBS, as the earlier version of that system, doesn't have that same kind of compression from a performance standpoint. So I read a great article, I don't know if you were able to read it, but Steve Newman from Scalar is here to present some of his information about benchmarking and analysis on standard EBS. So I'm going to flip back to that. Everybody give Steve a quick hand. There we go. Yeah.
Okay. So yes, my name is Steve Newman. I'm from a company called Scalar, and we're building server monitoring software and trying to kind of push the envelope a little bit on performance and scalability in the system we're building. And for us, as with a lot of systems, that kind of performance work, a lot of it comes down to I/O performance. And we're building on top of EBS, so as we were designing our system, we found ourselves asking a lot of the questions that Miles was alluding to earlier about, exactly how does this thing perform? As Miles was showing us, in that very nice slide, which is kind of EBS, a physical drive, and that big not equal in between. EBS has all kinds of nice properties, but it's not the kind of traditional hard disk storage that many of us are familiar with. And so we had all these questions, what kind of performance should we expect, and what's going to work well, or what might not work as well. We couldn't really find the answers we wanted, or we realized we didn't know the answers. We looked around, we couldn't find the answers, so we decided we'd better go get the answers. And so that led to a big project that we did to benchmark EC2 I/O performance in a bunch of different scenarios. I don't have time to go through all of that today. At the end of my little segment, I'll give you a link. What I am going to talk about a little bit, and is probably more important than our specific results, is the kind of methodology that you need to go in with if you want to understand performance of something you're building on top of EBS. And as Miles was alluding, fire off one little test, watch it print out a number at the end, and declare victory is not going to turn out to be a great methodology. Okay, so really, I'm going to go into some detail, but really I'm just going to try to tell you a couple of things here, convince you of a couple of things. When you're doing engineering, if you want to do it right, you need good data to base your decisions on. And in the cloud, on top of EBS in particular, and a lot of other things, you really need to make measurements, and you need to make multiple measurements. When you're testing something, when you want to see, does this work or how does that work, you want to be thinking about making multiple measurements and putting them together, not just running a test and looking at the one number that comes out as you might be used to. So, but let's take a brief step back. Why do we bother doing performance tests when we're doing engineering? Well, there are really a bunch of reasons, all the way through the life cycle of a project. Early on, you're making assumptions about, you're building on top of some platform, whether it's EBS or RDS or whatever it is, and you're making assumptions mentally about how that performs. It's going to be in this ballpark, it's going to vary this way or that way as I do this thing. And those assumptions may not be correct, but a performance test will really validate that for you. Then as you go along, you're making choices and design decisions. I can optimize this way or that way. Maybe I should be using a different instance type. And again, a performance test is your best tool for accurately making that decision. And then as you get farther along, maybe you're ready to launch, or you're getting ready to launch, or you've launched and you're wondering about capacity. Now you're doing a load test, which is again a kind of performance benchmark. So we like to think of performance benchmarks as being controlled experiments. You conduct a test, you get a result, and then you change something. Maybe you try a different instance type, or you tune a little bit. You run the test again, you get a new measurement, and you compare those, and that tells you the effect of the change that you made. So I've just sort of schematically sketched out a little example here. We've got our application that we're running running some application under some workload on two different, say, EC2 instance types. And we find on the first instance type, we run our test, and we see it sustained 103 operations per second. We try it again on a different instance type, and we get 152 operations per second. And so we conclude that the second instance type gives us about 50% better performance. So that's a nice, tidy conclusion. So I'm going to ask the question, is that valid? And probably not. And the trouble is, when we run a test like that, we're measuring a lot more than just our application. We're really measuring an application with some tuning of that application on some workload, on a particular instance type, which we've configured in a particular way. It's in a particular region and zone, on a particular instance in that zone, at a particular time, a particular state of the cluster network and the EBS volumes and whatever other backend systems we're working on. There's a very complicated picture here. And when we get our little 153 operations per second number popping out at the end of our test, all of this big complicated system went into that number. And so, it's dangerous to assume that, the one variable you're interested in was the one factor that really determined that number. So translated back into the kind of scientific language of a controlled experiment, what does that mean? It means we don't control all of the independent variables in our experiment. This chart kind of illustrates the problem. So here, I took 4 very simple I/O benchmarks and ran them on 4 EC2, EBS-backed EC2 instances. And so here we're just bar charting the results. So all of these, each of these 4 instances had the same configuration. It was an M1.small EC2 instance backed by a single EBS volume. You can see the results were really very highly variable. On one of the tests, the third chunk of bars from the left there was a ratio of 3,000%, 30 to 1, between the best and worst of the 4 instances that I'm presenting here. Even on the most stable benchmark, the large reads benchmark, there was a 50% variation from the best to worst instance. And 50% is a lot, right? That's, if you're making some decision, should I retune this way or should I try this other thing? The real effect you're trying to measure may be a lot smaller than 50%. So if you have a 50% error bar and you just measure once, you're really just flipping a coin. Now, I should say on this slide, I was going a little bit for shock value. I was trying to highlight my point. So I did deliberately seek out an example where the variations would be large. And in these 4 instances that I'm presenting you, I originally ran this test on 45 instances, and I'm showing you 4 that spread kind of from the best from the worst. So I've stretched a little, but not much. I didn't have to go looking for some very exotic configuration to find an example where you'd get these large variations. So one lesson you might take from this is if you care about consistent performance, don't run your system on a single non-provisioned IOPS EBS volume, and that's probably valid. But really, the deeper and more general lesson is that the cloud is a turbulent, noisy place, and there are a lot of things you can do to reduce variance. Provisioned IOPS are a great tool for that, but you should always assume that some noise is going to creep into your system somewhere, even if it's not from EBS. There's going to be noise in your system. And so you need to think about that when you're interpreting your performance tests. So what do we do about this? The answer is really very simple. When you're running a performance test, you need to run it multiple times, and very preferably on different instances at different times. And really, that's the entire takeaway from this segment, is run your test multiple times, or multiple copies on multiple occasions, different instances, different points in time. And so what you're going to get now is, instead of one number, this configuration 103, that configuration 152, you're going to get a whole collection of numbers. And if you just pull the median or some other kind of average out of that, you'll kind of hide, you'll wash away a lot of that variability, and you'll get a number that's more honest and repeatable, that you can rely on a little bit more, that you've averaged out some of those unwanted independent variables, like the state of the network, and hopefully you're really just measuring the one independent variable you were looking at, the new tuning or the new optimized code or whatever other factor you're trying to test. What's also interesting is from that same collection of numbers, by looking at the variability across all those numbers, you get an idea of how stable your system is going to be in production. If your numbers are all within 5% of each other, that tells you one thing. If there's a lot more variation in your test results, then that tells you there's probably going to be a similar variation in your production performance, and that's something you need to know. You may want to see whether you can mitigate that or just be prepared to understand that it's going to be there. But that's very important information, and it's nice to get that information early on during tests rather than kind of a trial by fire in your production system. All right, so that's about as much detail as I can go into in this quick little segment. Thanks again for Miles to give me the chance to come up here and speak today. As I mentioned, all this came out of a relatively extensive project we did to benchmark EC2 and EBS I/O performance. And I've given you the link here on a slide that you're not going to be able to look at later because my slides didn't get into the published slides, but you can find it at blog.scalyr.com. That's SCALYR. So if you're interested in that, it goes into more detail about a lot of things we found about specific configurations, specific instance types. It also talks more about kind of the ideas behind this methodology. What do you want to do if you're really trying to run a performance benchmark and get numbers you can trust? So blog.scalyr.com.
Great. Everybody give them a hand. So if you look at the workload that Steve was looking for, he was really trying to understand the performance and the behavior of our very smallest instances. And I think the analysis that you did was very sophisticated, and we really appreciate the hard work. We're working together with Steve to, it was unfortunate timing. The wrap-up of his testing was several days before the launch of provisioned IOPS. Just a bummer. So we're hoping to have him rerun some of those tests and get a better look at what it looks like on the newer systems. But everybody appreciates your help. What it seems like at this point, we've gone through, showed a couple quick demonstrations, talked through the performance of standard EBS and provisioned IOPS EBS. We're confident at this time, as a result of the hard work that the EBS teams put in, that we have a storage subsystem, a POSIX storage environment that allows high performance on relational databases, on NoSQL databases, on data warehouses, on your big files, on your media. They're the right disks to use out there for the right services. And we're looking forward to, I think all of the solution architects are looking forward to answering your questions about storage performance, answering your questions around storage configurations for your specific workloads, and helping you work through to get to the best design that you can so that you can continue to innovate and reinvent. Thank you very much for taking the time. I know it was a bunch of different stuff. Thanks everybody for attending the talk.